On April 28, 1988, Aloha Airlines Flight 243 took off from Hilo for what should have been a standard 40-minute island hop to Honolulu. It was a routine Thursday afternoon for the Boeing 737-200 and the 95 people on board. But 20 minutes in, cruising at 24,000 feet, the aircraft suffered a violent explosive decompression. With a deafening roar, the ceiling vanished. An 18-foot section of the upper fuselage tore entirely away from the plane. Just behind the cockpit, passengers were suddenly subjected to 300 miles per hour winds and sub-zero temperatures, while one flight attendant was tragically swept out of the cabin. Despite severe structural damage and almost non-existent flight controls, the pilots managed to keep the battered airframe flying long enough to execute a harrowing yet successful emergency landing on Maui. The survival of 94 people that day is incredible, but the engineering community was left staring at a terrifying paradox. Modern commercial airliners are engineered with built-in fail-safes. Specifically, they utilize structural tear straps designed to contain and isolate a crack so that localized damage doesn't spread. How did an entire 18-foot section of the roof bypass every single safety mechanism and unzip from a modern jet in midair without a single warning? When the National Transportation Safety Board opened their investigation, they immediately checked the aircraft's history. It was 19 years old and had accumulated over 89,600 flight cycles, meaning takeoffs and landings. That gave it the second highest cycle count of any 737 in the world. The plane spent its life flying short inter-island routes in Hawaii. This meant it was subjected to constant rapid pressurization and depressurization cycles, all while baking in a corrosive, salty, and humid tropical environment. This diagram shows the point of failure, the fuselage lap joints. These horizontal seams fasten overlapping aluminum skin panels. Boeing used a cold bond process, gluing the metal sheets with an adhesive epoxy alongside the rivets. But early models suffered from poor bonding quality over thousands of flights. This weak adhesive degraded and failed, allowing moisture and corrosive sea salt to wick directly into microscopic gaps between the metal plates. This triggered hidden localized crevice corrosion inside the seam. That salt water slowly ate away at the joint's foundation, weakening the bond and transferring the immense stress of a pressurized cabin onto a microscopic threat. To understand what actually tore the plane apart, we have to zoom in on the individual rivet holes running along that corroded seam. Because the 737's aluminum skin was extremely thin, these holes were countersunk, beveled inward, so the rivet heads could sit flush against the exterior for aerodynamics. This cross-section shows the geometric flaw. The beveling tapered the metal to a sharp point or knife edge. During cabin pressurization, stress concentrated onto these razor-thin edges. Normally, this creates one isolated fatigue crack, but here, the knife edges, high stress, and corrosion triggered multiple site damage. In the bottom diagrams, multiple site damage means microscopic fractures nucleate at dozens of adjacent rivet holes simultaneously. At 24,000 feet, these cracks linked up, bypassing the tear straps. The simultaneous union of thousands of fractures unzipped the airframe from the inside out. There is also a chilling footnote in the NTSB report. As passengers were boarding Flight 243, one woman actually noticed a crack in the fuselage near the door. Assuming the crew already knew about it, she didn't alert anyone. But the airline's highly trained mechanics didn't know at the time. Visual inspections of the fuselage were typically scheduled late at night. Spotting hair-thin surface cracks along a dirty overlapping joint in the dark was virtually impossible. And as this chart shows, multiple site damage doesn't give you time to find it. Unlike normal fatigue, which causes a gradual, predictable decline in a plane's structural integrity, multiple site damage causes residual strength to plummet violently and suddenly below critical safety thresholds. The NTSB report targeted the global maintenance philosophy itself, labeling visual inspections inadequate for the hidden stresses of an aging worldwide fleet. The fallout was immediate. Boeing completely abandoned the cold bond process for its aircraft, and the FAA rapidly assembled a massive task force to address the looming crisis of aging airplanes. Regulators realized that simply ordering mechanics to look at planes more frequently wasn't going to stop the next disaster. Human eyes could not compete with microscopic metal fatigue. The industry pivoted to a strategy of absolute action. Airlines were mandated to proactively replace aging structural parts based purely on flight cycles. Furthermore, they were required to use non-destructive testing, like electromagnetic eddy current scanners, to detect invisible internal fractures before they could ever link up. Aloha Airlines Flight 243 remains a terrifying milestone in aviation history. But the engineering autopsy of that torn fuselage forced flight safety to evolve from a reactive visual process into a proactive microscopic science, ensuring that the invisible limits of metal fatigue are never crossed again. End of report.